All right. Hello, welcome. Let's get started with the first part of 4.1. We're going to look at an example here of what we call a difference equation. And a difference equation is the same idea as a differential equation. And there is a difference between difference equations and differential equations. We'll talk a little bit about that. But the gist of it is that when you have a number of different quantities whose amounts are changing, but the rate at which they're changing depends on the amounts of the other quantities. You could represent that situation with either a difference equation or a differential equation, depending on the situation. And that kind of thing is so common in any application of math where the amounts of things depend on how much of other things there are. It has a gazillion applications. I'll just leave it there. But let's look at one. All right. So Lieutenant Spock accidentally transports a population of 100 baby tribbles, which are these cute, furry little creatures. He accidentally transports them to an alien planet where there's plenty of food, but also some predators. Every week, 80% of the baby tribbles are eaten by the predators, but the other 20% grow to become adult tribbles. So, in other words, the number of adult tribbles depends on how many baby tribbles there are. And also, when you have 80% of the baby tribbles being eaten, the number being eaten depends on how many there were the previous week. And also, every week, every adult tribble gives birth to 5 baby tribbles. So the number of baby tribbles depends on how many adult tribbles there were last week. And at the end of that week, 60% of the adults are eaten. So we're going to represent with a vector the values of these variables, the number of baby tribbles on that week and the number of adult tribbles. And we're starting on week 0. There are 100 baby tribbles and 0 adults. So we're going to do part A. We're going to find x1, x2, and x3 first. Maybe we can start with x1 over here, and then we'll move to the other side when we need the room. To get what is x1, in other words, we want to know how many baby tribbles there are and how many adult tribbles there are after 1 week. Well, what happens to the 100 baby tribbles that there were the previous week? Well, 80% of them were eaten, and the other 20% grow to become adult tribbles. So that tells you that the number of adults the next week is going to be 20% of 100. And the number of baby tribbles is going to be 0 because all of the baby tribbles last week were either eaten or grew up to become adults, and there were no adult tribbles to give birth to new ones. So yeah, x1 is just going to be the vector 0, 20. So now there are 20 adult tribbles and no babies. Let's move over here to find x2. So this is the number of baby tribbles and adult tribbles after 2 weeks. And first, let's think about how many babies there will be. What are we going to put right here? Well, how do you get babies? What we have is 20 adults the previous week. And we know every adult tribble gives birth to 5 baby tribbles. So we're going to have 5 times a1 here. It's going to be 5 times 20. And then how many adults are there? Well, we would have 20% of the babies grow up to become adults. So we could say 20% of the babies will now become adults in the next week. But we know there weren't any babies the previous week. But I'll write this anyways just to show work. And then also, there's still going to be some of the adults that survive because every adult tribble gives birth to 5 baby tribbles, and then after that, at the end of the week, 60% of the adults are eaten. So we still have the other remaining 40%. of the adults from the previous week. So A1 was 20. 5 times 20 is 100. And there were 0 babies plus 40% of 20 is 8. All right, so now we have 100 baby tribbles like we started with, but also some adults. So let's see what happens in week 3. So first, let's think about the babies. The only place babies come from is from adults. So this is going to be 5 times the number of adults in the previous week. So 5 times A2, which is going to be 5 times 8, which is 40. And then the number of adults, well, 20% of the babies grow up to be adults. And also 40% of the adults survive one more week. So that gives you 20% of 100, which is 20, plus 40% of 8. So now we have 40 babies and 23.2 adults. And I know you can't really have 0.2 adults, but just to smooth out the math, let's just say there's 23.2 adults. Let's look at part B. We want to find a matrix A so that the vector that tells you how many adults and babies there are 1 week is A times the previous vector. Well, to do that, maybe let's see what did we do here. Like to get x3, can we think of this as a matrix times the previous week's result? So that would be B2, A2. So what would go in these numbers here to make this work? Well, let's see. We could say when we're doing matrix by vector multiplication, we would be multiplying B2 by whatever this first column is. And we could do B2 times 0 and 0.2. And we could also do A2 times a vector 5.4. Like so. Maybe I could highlight this differently. So this is saying that the first row here tells you how to get the next week's baby population. And you get the next week's baby population just from 5 times the adults from the previous week. And to get the next week's adult population, we have 20% of the surviving babies and 40% of the surviving adults. That adds up to get the next week's adult population. And the column that they're in, like this being column 1 and column 2, that tells you that you're multiplying that column by the previous week's baby and adult population. So yeah, in other words, we're saying that 1 week later's, whatever week W is, the next week we can always get by doing the vector 0.2 times the previous week's baby population. And we can add to that the vector 5, 0.4, multiplied by the previous week's adult population. And we saw examples of how that formula works here. So that matrix there is our A. And I just noticed there was also a little typo here. That was A2. It said A3 before, but that was a mistake. Of course, we're doing the previous week's, which was B2 and A2 here. So anyways, that was A2. Let's look at part C. Use a computer to see what happens to the tribble population in the long run, like as the number of weeks approach infinity. Like, do they continue multiplying and growing forever, or do they all get eaten by predators, or what happens? Now, to do that, like we know how to get x1, we can say x1 is a result of doing a times x0, and we know that the x0 was 100, 0. And once you have that, you can plug that in to get x2, because x2, using this fact that xw plus 1 is always equal to a times xw, x2 is going to be a times x1. And once you have that, you could find x3 is a times whatever that x2 result was. And you could keep doing this for a long time, just repeatedly multiplying by a. But repeatedly multiplying, isn't there another way to describe that? We can call that exponentiation, right? So how do we write this as exponents? Well, the a times x1 thing here, we could think of as a times x0. And you could just write that as a squared times x0, like so. And then you could plug that in here for x3. We're doing a times a squared times x0. Of course, we could think of that as a to the power 3 times x0. You see where this is going. Like every time you go up by 1 week, you're just multiplying the previous week by a. So in week W, we're going to get a to the power w times x0, following this pattern. So that is going to be an easier way to like think about this. Like, and the a to the power w really does still just mean multiply by a w times, just using sort of a more condensed notation. Now to figure out what this is with a computer, I know we are not really using any software things in this class, but this is what it looks like when you use Python with SymPy loaded. We're going to say A is a matrix with one row that is 0, 5, and another row that is 0.2, 0.4. And then x0 is a matrix with 2 rows and 1 column. So I can just write a times x0 here, and we get 0, 20. That was the x1 we got before, right? 0, 20. To get x2, let's just check that we do get the 108 that we want. In Python, you write exponents as with 2 asterisks, so that means a squared, that times x0. Yeah, we get the 108. If we do a to the power 3, we get the 40 and 23.2. And this is where a computer comes in handy, because repeatedly multiplying matrices by each other is what computers are really good at. It's specifically what GPUs are designed to do. I don't have any kind of fancy GPU in this computer, but it's still easy enough. So let's say after 52 weeks, it's been 1 year, what happens? Oh, we have 1.23 million triples that are babies, and also 300,000 adults. Okay, what about after 2 years? 104 weeks. These numbers just keep getting bigger. What about after like 1,000 weeks? Okay, now we have 7.83 times 10 to the power 87. So at this point, there's like more tribbles on this planet than there are atoms in the observable universe. So I think it's pretty safe to say that limit as w approaches infinity, we can see it's going to be basically infinity, just for both the baby and adult tribble populations. So we could write that way. Now, there's other questions you might ask about it, like, is the ratio of adults to baby tribbles always going to be about the same? Let's see if that's true here. Like if you do 1.912 divided by 7.83, okay, that's about 24%. Also, if we take, so this is after 2 years, yeah, we still get about 24%. So it seems like we're not just getting numbers that are growing without bound towards infinity. It seems like there's always about 4 times as many babies as there are adults. So it turns out there is an eigenvector here that we will explore a little bit later. Okay, so a few things to notice about this is like if this was an actual alien planet and if Star Trek was real, then the population of tribbles wouldn't grow to infinity for a bunch of reasons. Like the most obvious one is that the food supply on the planet is not infinite. Eventually, the food supply is going to get lower. Some of the tribbles are going to starve, and the food will hopefully replenish itself if there isn't a complete ecological collapse. But that's another thing. The tribbles' food supply itself depends on how many tribbles there are eating it. So that could be like another variable in this difference equation. Another thing is that the population of predators would also increase as long as they're well fed. And the more predators there are, the smaller a percentage of tribbles survive to reproduce. So there's always a weird balance going on between the populations of the predators and the populations of the prey. And this is a thing that happens in the real world. And also, over the thousands of years, there would be evolution happening. So their abilities to eat and reproduce would be changing as well. And so maybe this isn't always going to be like 60%. So all of these things can be represented by more complicated versions of this kind of linear difference equation. Now, in the real world, there are things that are not linear, like there's non-linear difference equations too, and that's when things get really hard and complicated. But a linear difference equation is like a foundation of how to explore that stuff. Sort of like y equals mx plus b is a foundation for studying calculus. In the next video, we're going to look at a new virus emerging in a population, another kind of example of this linear difference equation. So I will see you then.